Hey, 11th graders. So we are starting our last lesson of this unit. And this lesson is kind of where you're going to be able to see all of the things that we've been doing so far all come together with one application. And that application is Voronoi diagrams. So this unit hasn't really felt very applicable, hasn't felt very applied at all yet. And it's because we've been learning all of these background pieces of information to be able to apply to this one big application. Voronoi diagrams. So I'm sure you have at some point, or you will at some point, be like looking at a map, like your Google Maps, and you're saying, like, okay, here's the M3 stations, the M3, and you're saying, like, okay, I want to know which metro stop is the closest one to me. Or maybe you're looking at bus stop stations, or maybe you're looking at the grocery stores that are surrounding your house or apartment, and you're trying to figure out which one is the one that is closest to me. And Voronoi diagrams kind of addresses that question of which one of these things is closest to me. So imagine, if you will, if this right here, this is a Voronoi diagram. It looks something kind of scientific almost. But imagine if you have like a map underneath this, and then each of these cells could be like streets, right? You could have streets like within the cells, and maybe you live like here, and you've got a grocery store here, and you've got a grocery store here, and you've got a grocery store here, and you're trying to wonder like which one is closest to you. And we can see on this Voronoi diagram, well, obviously this is the grocery store that is closest to where you live. So that's the grocery store you should go to. But maybe if there weren't all of those cells split up, you wouldn't know which one is closest to you. It'd be hard to find out. And so that's kind of what these do. We have a couple of vocabulary words. Each one of these dots is called a site. So you'll hear us refer to it as a site. And a site is individual coordinates representing a single location. So they could be restaurants, they could be airports, they could be water fountains, they could be anything, right? And so they're representing an individual thing on a map. And then they're surrounded by these lines, and each of these lines are called edges. They've got these edges, and the edges are actually perpendicular bisectors between all of the sites. So, something we've learned earlier in this unit, perpendicular bisectors, right? So, look between these two sites. Notice that this guy is the perpendicular bisector between those 2 points. This guy right here is the perpendicular bisector between these 2 points. Pick any edge and see if you can figure out which one is it, which 2 points are being perpendicularly bisected by that line, right? This guy right here is part of a perpendicular bisector between this point and this point. This one is the perpendicular bisector between this one and this one. So all of those lines are perpendicular bisectors between two sites, and it fences the cell. So a cell is the like bubble that surrounds that site. So this whole guy is a cell. We also call them regions. Everything in the cell is closest to the site in the cell. So if you lived here, any other point that you can put within this cell would have this site being the closest site to you. If I lived in or was placed in this cell, this site right here would be the closest site to me. So the cell region establishes the region in which that site is the closest site to you. The last thing that we care about are all of the intersections between these perpendicular bisectors, all of the edges, the corners, right? So this guy right here, for instance, is the corner between perpendicular bisectors. This guy is the corner between perpendicular bisectors. This guy is the corner between perpendicular bisectors. They're called vertices, or a vertex, singular, vertices, plural. And a vertex is your intersection between perpendicular bisectors. The cool thing about these intersections between the perpendicular bisectors, if you remember from our definition from perpendicular bisectors from previous lessons, the perpendicular bisector is the set of all points that are equidistant from two other points. So every point along this line is equidistant to these 2 points, right? So if I'm looking at intersections between perpendicular bisectors, I find one point that agrees on being equidistant from a bunch of other points, a few other points. So every single point on this line is equidistant between these 2 points, and every single point on this line is equidistant between these 2 points. Well, if I found the intersection, I found the one place that is equidistant from this point and this point and this point. It's hard to see, but you could draw a circle with the center at the vertex. This is a compass. We don't use them much in IB, which is a shame. I think they're fun, but I'm a math teacher, so I'm biased. If I center my circle, the pointy part here, at the vertex, and then I make my radius, the distance between the vertex and the site, I could draw a circle which I just did. I just had to take it away for a second, that represents that radius. And notice all of those points are on the circle, right? So that means that this is the only point that is equidistant between those 3 other sites. So equidistant from sites. And we could imagine, or at least believe, that I'm going to explain to you at some point why we care about having points that are equidistant from a bunch of other points in terms of this application. But right now, that's the vocab that you need to have, the understanding of a Voronoi diagram being this idea of like a map representing spatial proximity. This idea of spatially, how close are you to things? That's what a Voronoi diagram is. Heads up, I think a Voronoi diagram is a super fun and cool thing to do for your IA. I think it would be something that's really interesting. And so I encourage you to think of something in which you could apply this for. And remember that Thinker is our SSI for this unit. And so trying to think about ways that you could apply this in a bunch of different ways, whether it's in a different class or whether it's in your day-to-day life. This could be a really fun way to expand and look deeply into something going on in your life for your IA. Okay, so let's just practice with Voronoi diagrams for a second. This is a Voronoi diagram that is already made. We've got a bunch of points in here. You will be eventually asked to make Voronoi diagrams. Typically not one of this size unless you do it for like an IA. But you've got all these different sites, and all these different sites have no application. It's just a Voronoi diagram. It says identify the site that is closest to the coordinate 30, 20. So we go to the 30, 20 mark. Here is 30. And we go up to 20, which is, that's so hard to read here, I think. Yeah. That is the point 30, 20. Which site is closest to that coordinate? Since A is in the same cell as that coordinate, A is the closest site to that point. So A is your answer. This ability to find those values is called your nearest neighbor interpolation. Kind of a strange phrase for just saying, like, we take the nearest neighbor and we say our value is the thing that is closest to us. That was not a good explanation. We take our nearest neighbor and assume that we fall under the same category as our nearest neighbor. So we'll look into that later and I'll give you a better definition. But that's your nearest neighbor interpolation. It says give the coordinates of the vertex equidistant to 4 sites. So we've shown earlier one being equidistant from 3 sites. Notice it's 3 perpendicular bisectors all coming to meet in one point. So it's pretty common to have 3 perpendicular bisectors all meet at one point, right? It's typically because this is a cool geometry math thing. But if you find what's called I think it's the circumcenter, but it's your point of concurrency of all the perpendicular bisectors, throwing some fancy math terms out there, no big deal. But if you take a triangle and find the perpendicular bisector of all 3 sides, if you draw where the perpendicular bisectors all meet, creates the center of the circle that would intersect all 3 of those points, right? So I could draw a circle at any 3 points. So it is guaranteed mathematically, it's proven that any 3 points, if you find the perpendicular bisector between all 3 of those points, it will always meet at one point. So it's guaranteed that you will have points that are equidistant to 3 sites. But we're now looking for one that's guaranteed, or not guaranteed, just one that's equidistant from 4 sites. So we're looking for a place that intersects between 4 perpendicular bisectors, which is abnormal. We can see this is 3, 3. They're close together, but that's a point, and then that's a point. They're 2 separate points. So those are just both 3, 3, 3, 3, 3, 3, 3, 3, 3, 4. These are 4 different perpendicular bisectors. 1, 2, 3, and 4. This coordinate right here is where 4 perpendicular bisectors meet, which means it's equidistant between 4 different coordinates or 4 different sites. That site has the coordinate of 25. Okay, it says estimate the coordinates of a point equidistant to sites A, E, and K. So I like to visualize the triangle AEK. AEK. And I'm trying to find the perpendicular bisectors of all 3 of those points, here, here, and here. And the point of intersection between them is about here. So we're going to guess what that coordinate is, or not guess, but estimate, educationally guess. And it looks to be 19 as my x value. And like maybe 26, but a little bit more. So I'll say like 26.5. If you had said 26, fine, because it says estimate, so it's allowing a little bit of wiggle room. If you had said 27, fine, for the exact same reason.